Hey guys, Assalamualaikum. Welcome back to another virtual lecture. In this video, we will learn about the second application of the F distribution, which is to compare several population means simultaneously. This test is also known as the analysis of variance, or ANOVA. Some of you may be wondering what's the difference between ANOVA and the population means test that we've learned before. Let me show you some of the differences. First of all, when we learned about the population means test before, it is to test whether or not two population means are equals to each other. Okay, recall step 1. When it was a population means test, we wanted to see whether, both population means are equals to each other, right? As opposed to the alternate, which says that there is a difference between the two. Or of course, this sign may be greater than or lesser than, depending on the question. And if the population means test involves small sample sizes, we used the pooled t-test. Both of these tests want to compare the difference or the similarities between two population means. The difference is, for this two-sample population mean test, the sample sizes are large, whereas in this test, the sample sizes are small. And normally when it's a small sample size, we do not know the population standard deviation. Okay, so that is why here, for the step 3, let's just compare. When we want to calculate the test statistic, here we will use the Z distribution, and here we will use the T distribution. So how are they different from the ANOVA? ANOVA, the objective of the test is similar, which is to test the difference or similarities, or in other words, the equality of population means. But this time it is for 3 or more population means, okay? So just remember, if you've only got 2 samples, it's either these 2 tests. It's either the 2 independent sample population mean test or the pooled t-test. But if you've got more than 2 samples, 3, 4, 5 and onwards, we will use ANOVA. Here's an excerpt of my lecture notes. I want to show you the assumptions that we have to make before we can conduct the ANOVA test, okay? So first of all, we need to assume that the populations from which the samples are selected must follow the normal distribution, okay? And then we also assume that the populations from which the samples are selected must also have equal variances. And finally, we assume that the observations from each sample must be randomly selected and independent of each other. Let me give you an example of an ANOVA test. See, these are 3 of the public universities in Malaysia: IIUM, UM, and UKM. Right? So as you can see, these 3 populations are independent of one another. Say we want to compare the starting salaries of fresh graduates from these 3 universities. Okay, as always, instead of doing a census or asking all of the population items, what we do is we collect a sample, right? So here's a sample of IIM students, N1, and here's a sample of UM students, N2, and here's a sample of UKM students, N3. So from these samples, what do? We can calculate the average starting salaries, right? And here also we can get the average starting salaries for UM fresh graduates, and here we can get the average starting salaries for the UKM fresh graduates, okay? Now remember, the objective of taking these sample means is because we would like to estimate the population means. So here would be the actual or the true value of average starting salary for IIUM. Here would be the actual or the true value of the average starting salary for UM. And here would be the true value or the actual average salary for UKM students. Okay, but as we know from previous topics, it's difficult for us to actually get these values, right? Because the only way to do so is to conduct a census, which is to study each and every item in the population. Okay, so we've established that fact that although this is ideal, it's quite impossible to get. That is why we use their best estimates, which are the sample means. To know how to write the hypothesis, we must understand one thing: the closer these sample means are to each other, the more evidence that we can conclude that the population means are close to each other. Likewise, the more the sample means differ from one another, the more evidence we can conclude that the population means are also not equal or different from each other. Okay, so for step 1 of the ANOVA test, this is how we write the hypothesis, okay? Because remember, the null hypothesis always assumes equality or no difference between the population means. So remember just now, 1 is IIUM, 2 is UM, and 3 is UKM. What this means is, okay, please pay attention to the first, or the null hypothesis. What we're saying here is there's no difference between the average starting salaries of the fresh graduates in these 3 universities. Okay, if you notice, I put an equals to ... because it might be more than 3 samples, okay? So our example just now was only 3 populations, therefore 3 samples, so we can just ignore the rest. But if for whatever reason in the exam you're asked more than 3, please feel free to write equals to mu4, equals to mu5, etc., and so on. Okay, so this is the null hypothesis. In contrast, the alternate hypothesis is just writing the population means are not all equal, all right? Because we are not sure which population means are equal to each other or not, okay? And that is not the objective of ANOVA. ANOVA just wants to test whether all of the population means in questions are equal to each other or not. Okay, so we just want to make it very general, and that's how we write it. Sometimes we can also write at least one of the population means are not equals to each other. Okay, to recap, the closer the sample means are to each other, the more evidence we can say that the population means are also close to each other. When the averages are close to each other, in other words, there is no difference between them. And that is what our null hypothesis is all about, right? That is why when we say there is no difference, what it means is our variability or the difference, dispersion, spread between the means are small, we are supporting the null hypothesis. In contrast, if the sample means differ from each other, we have more evidence to suggest that the population means also differ from each other. Differ means we've got a large variability. What that means is we have more evidence to support the alternate, which means the population means are not equal to each other. Step 2 is the same, that is to write down what our alpha or level of significance is, and this information is normally given in the question. However, there's a big difference in how to calculate the test statistic. Now, say there is a difference between the starting salaries of these 3 institutions. Now, there are 2 differences. Okay, one is the differences between the groups. Between means the starting salary on average for IUM students would be different from the average starting salary for UM students. May be different with the average starting salary for UCAM students. So this is what it means by differences between groups. Besides that, there's also differences within the group. What it means is, let's zoom into IIUM case only. Now, within this sample, okay, there are also differences among the starting salary, right? One person's starting salary may be different from another person's starting salary, but they're all IIUM students, okay? So this is what it means by the differences within the group itself. So when there's a difference in the starting salaries between these 3 institutions, sometimes we can explain the differences. Maybe one of the institution has better facilities or better lecturers or maybe more grants given by the government. So those type of differences can be explained. In other words, when the differences arises between the groups, the differences can be explained. Okay, so it can be explained. Whereas the differences that arises within the groups, such as here, sometimes it's not that easy to explain, because how can fresh graduates from the same institutions receive very different starting salaries? They're all being taught by the same lecturers, they experience or use the same facilities, so why are there still differences in their starting salaries? So that is why, since the differences is difficult to be explained, therefore differences that arises within the groups cannot be explained. Okay, to recap, we've got total differences, right? Total differences in starting salaries just now between the 3 different institutions. So these total differences can be divided into differences that arises between the groups, okay, between IIUM, between UKM, and between UM. And there's also differences that arises within the groups. Okay. And I've also mentioned to you just now, the differences that arises between the groups can be explained, right? Okay, can be explained. Okay, whereas the differences that arises within the groups is a bit difficult to be explained. So therefore, we write it as cannot be explained. Now, let's say we change the word. All of these differences, we change it to variation. Okay, so because they mean the same thing. All right, so let's say they are, so in other words, the total variations, it can be divided into two, right? The variations between groups. So normally we write it as variations that can be explained or explained. Variance. And here are the differences or variations that cannot be explained. Or in other words, it's called the unexplained variance. There's another word that can be used to describe the differences between groups or differences that can be explained, which is treatment. Now, in order to understand why is the word treatment used, okay, let me tell you a little bit of story. ANOVA, okay, historically, it was actually first used and developed in agriculture. Okay, so what it means is back then there were plots of lands that perhaps the farmers wanted to test, right? So here are all the plots of lands. So if they wanted to test a particular fertilizer or pesticide, so what they do is they're going to be putting it on a particular land. So this land that they actually put all of those pesticides or fertilizers, they are called the lands which are being treated. Okay, treated. Therefore, the term treatment is very much symbolic of the usage of ANOVA. So although these days the applications of ANOVA is far and wide, okay, it goes on beyond agriculture, but maybe due to symbolic or sentimental reasons, the term treatment is still being used. Okay, why am I saying this? It's because normally when we conduct the ANOVA test, you may come across terms that are not these two. Okay, sometimes when we want to calculate the test statistics, you don't see the words between groups or explained variance. Instead, what you see is treatment effect. So at least now by telling you the story, I hope you understand why is the word treatment suddenly there, because it's out of nowhere, right? And here, for variations that cannot be explained, it is called error. Okay, why error? Because, you don't really know. Why is it? I mean, everything else is being accounted for. All of the students are being taught by the similar lecturers at the same university, the same facilities, but there's still differences in their starting salary. So it's something that you cannot explain. Maybe something out of our control, something that is due to by chance or out of control. We normally put it as error. Okay, so here, as you can see, the terms, it means the same thing. Differences that can be explained are called explained variance, or between groups differences, or treatment effects. Whereas variations or differences that cannot be explained are called within groups differences, unexplained variance, and error. Having learned about the history of ANOVA as well as the origins of the terms important in ANOVA, now it's time to learn about the formulas used. Remember that to find the variance, we need to take each and every value of the random variable minus the mean, and then we need to square it and add them all up. So up here is called the sum of squares. Okay, and then we divide it by our degrees of freedom, n minus 1. Okay, so this is variance. All right. So you can refer back to topic 2 under describing data if you have forgotten or not sure about this variance. Now, as mentioned to you before, this variance or total variance is divided into two, right? One is the variance that can be explained and another is variance that cannot be explained. Okay, so here is our total variance or total variation. Okay, divided into two. Variance that can be explained, explained variance, or the treatment effect. Here's the unexplained variance or the error. So as you can see, slowly and slowly we are leaving the usual terms of between groups, within groups, and using the terms associated with variance, yeah? These three, they are all variance. Okay, so what it means is, if you want to find what is the formula up here, it has to be similar to the total variance. Now you can see here, the total variance formulas consist of two parts, right? So the first one up here, right? The first one up here is called the sum of squares. And because it's total variance, up here is actually called the sum of total, right? Down here is the degrees of freedom for the total variance. Likewise, when we want to calculate the variance or the explained variance, it also consists of two parts. Okay, one is called the sum of squares due to treatment over the degrees of freedom for the treatment. And down here, to get the unexplained variance, also divided into two parts, which is the sum of squares for the error over the degrees of freedom for the error. All right? Now, to present all of this in a more organized manner when we do the ANOVA test, we can translate all of this into what we call the ANOVA table. Okay, so to construct the ANOVA table, first of all, we need to determine our sources of variation. Okay, this is the first thing that I showed you just now. So there are two sources of variation, right? One is due to treatment. In other words, this is the differences that can be explained. This is the difference that arises between groups. And then another source of variation is due to error. In other words, this is the differences that cannot be explained. This is the differences within groups. Okay, so you don't have to write all of those other terms. You just write it as treatment and error. And of course, when you add them together, you'll have total, right? Okay, so let's make this proper line. Okay. Now, as I mentioned to you just now, all of these are variance. And to construct variance, you've got two parts of the fraction, right? Of the ratio. At the top is the numerator, which is basically our sum of squares, right? And at the bottom is our degrees of freedom, right? Now, the sum of squares divided by the degrees of freedom, you can get the mean square. Mean square is basically the variance lah. Okay? So here for the treatment, just now at the top is the sum of squares due to treatment. For the error, it's sum of squares due to error. And of course, if you add them both, you can get the sum of squares for the total variance, right? Now here, I think we can write down the degrees of freedom for the total variance first, which is n minus 1, right? Okay, so here, this is n minus 1. Now for the treatment, this is slightly different. You need to remember. Now remember, treatment is basically the different groups, right? Remember our example just now? There are three different universities, IIUM, UM, and UKM. So those groups are also known as categories. Okay, so how many categories do we have just now? It was 3, right? So categories is denoted by the letter K. So for the degrees of freedom for the treatment is K minus 1. Now to get the degrees of freedom for the error is actually very simple. It's just n minus 1 minus K minus 1. Right, so if you open up n minus 1 minus K plus 1. So minus 1 and plus 1, you can delete them. So what's left is n minus K. So that is why the degrees of freedom for the error is n minus K. All right. Now, we just divide the sum of squares with their respective degrees of freedom to get the mean square. Okay, so SST over K minus 1, we can actually get the mean square due to treatment, right? And here, SSE over n minus K, we can actually get the mean square due to error. Now, why are we doing all of this, guys? Because at the end of the day, what we want is the test statistic, which is F, right? So F is basically the ratio between these two. So F is MST, mean square due to treatment, over the mean square due to error. And so this is how we get the test statistic for an ANOVA. In case you're wondering what's the difference between the F test statistic used in ANOVA and the F used in equality of variance test, is actually very similar. Now, if you look at the last video, I've shown you that the F is the ratio between two variances, right? Okay, the first variance over the second variance. Okay, only last time it was made quite general. Okay, I just told you that up here should be the larger variance divided by the smaller variance, but they're both variances. So it's similar, isn't it, to this? Both of these are variance. The variance due to treatment is obviously larger, because something that can be explained should be larger than something that cannot be explained, right? So here is actually similar, only now for ANOVA, the names are more detailed. Okay, it's called the MST, mean square due to treatment, over the mean square due to error. And last time in the equality of variance test, we just say it as the ratio between two variances. Okay, so here's the ANOVA table in your lecture notes. Now, the reason why I didn't show you this straight away is because I think it would be a bit more informative if I were to construct the table step by step instead of just, showing you the final product. So basically, you need to remember this in order to get the F test statistic. Now, the next question is how to calculate the SST and SSE or SS total. Now, the thing is, guys, you don't have to calculate the three of them altogether. What we need to find is just two. One is the SS total. Okay, we need to calculate the SS total, which is this formula. Okay, which is, if you've seen this, this is very similar to the numerator part of our variance, because remember, total variance here is the usual variance formula that we've seen before. So this is the numerator part, the one on top. Okay, so X here refers to all of the values minus the average. Now, you may notice that there's a G here. Okay, this refers to the grand mean. Okay, I'll show you later when we do example. So I repeat, each and every value minus the grand mean, square it, because we would want to get the sum of squares, right, for the total variance. Okay, so this is basically the SS total. Now, once we get the SS total, the next thing you want to get is the SSE. Okay, SSE, okay, this is how we get it. Okay, again, similar, each and every value minus the, okay, here you can see there's a subscript C here as compared here. Here is the grand mean, overall mean. Here is the mean that you get from each column. That's where the C comes in. What does that mean? Now let's look back at this example just now. Okay, remember these are our three populations or groups, right? We call them groups or categories. Okay, so this is the differences. So we can see that they are all different from each other. That's why we've got two differences, right? One is the differences between the groups. Another one is differences within each group. Now, as you can see here, we can actually, present them or visualize them as a sort of table, right? So we have a table here. So therefore, this represents one column. This represents another column. This is another column. So the thing is, this is basically your X bar subscript C. Okay, this is also X bar subscript C, X bar subscript C. So in other words, this is the average for IIUM. This is the average for UM. This is the average for UKM. Okay, so this is what it means by the sum of squares due to the respective column. Okay guys, so I'm putting all of these notes side by side. Hopefully you can understand. Here would be the overall or grand mean, which I'll show how to calculate later. But here are the respective column means, which are these ones. Once we have the sum of squares total and sum of squares error, we just minus them together. Okay, we just deduct SSE from SS total to get the SST. So in other words, you don't have to actually do them separate, all three. You just need to find this one and this one, minus them, you can get the third one. Once we have all of this information, we can write in the degrees of freedom, which is simple, and then we just divide them to get the respective values, and finally find the ratio of these two to get our F. And this is, guys, basically step number 3. Now, step 4 is similar. We just need to find the critical value so that we can come up with the rejection rule. Now, since we are using the F distribution, F is positively skewed, so the way to write the decision rule is always to reject the null if the F test statistic exceeds or more than the particular critical value, right? Okay, because it's always going to look like this. Okay, so we're always going to reject this area. That is why the way to write the rejection rule is always the same. Now, to find the critical value here is very simple. Well, you've already found it in the ANOVA table. It's here. Okay, because this is the degrees of freedom for the numerator, and this is the degrees of freedom for the denominator. See? This is our numerator, so we got this from this degrees of freedom. This is our denominator, and we use this degrees of freedom. So you just need to look these up in the F table to find your critical value. And finally, step 5 and 6 is to make the decision and conclusion. Let's take a look at this example of an ANOVA test. A physician who specializes in weight control has 3 different diets she recommends. As an experiment, she randomly selected 15 patients and then assigned 5 to each diet. After 3 weeks, the following weight losses in pounds were noted. At the 5% significance level, can we conclude that there is a difference in the mean amount of weight loss among the 3 diets? Okay, as you can see here, there are 3 plans. Diet plan A, diet plan B, and diet plan C. Now in this question, it's coincidentally all of the participants are the same. There's 5 to each plans, but it doesn't have to be equals, okay? So don't be surprised if you find a table that maybe here has only 5 people, and over there we have 7 people, and then there we have only 2 people. So they can be different, okay? It doesn't matter. Okay, it's just that in this example, it's coincidentally, it's the same. So I'm going to show you how to solve this, and you can take the time to do it with me. Okay guys, so let's do the 6-step hypothesis testing for the ANOVA test. Step 1 begins by writing down the hypothesis. As mentioned before, the null hypothesis always assumes equality or no difference between the population means, right? So there's no difference between the average weight loss between the 3 diet programs. So mu A equals to mu B equals to mu C, no difference. Alternatively, the alternate hypothesis states that at least one of them are not the same, or you can say that not all of the population means are equal. Okay, or you can also say at least one of the population mean is different. Okay, now step 2 is to basically write down what our level of significance is. So it's given that alpha is 0.05. Okay, now here's the long part, which is to calculate the test statistic. Okay, so we know that we will use the F distribution as the test statistic for ANOVA, and to do so is to construct the ANOVA table. Okay, so basically this is the ANOVA table that we want. Remember, it starts with the variation. Okay, so the ANOVA table starts with the source of variation, which can be divided into treatment and error. So when you add this together, we'll get total, right? Okay, maybe another line, another header. Okay, so to get the source of variation, okay, we have this. Now, the next column is the sum of squares. Okay, sum of squares for treatment is called the SST. Sum of squares for the error is known as SSE. Both of them, if you add them together, you get SS total. Okay, so I'm purposely giving a big space here so we can write down the figures later. Now the next column is the degrees of freedom. Okay, the degrees of freedom for the treatment is K minus 1. The degrees of treatment for the degrees of freedom for error is N minus K. Okay, so, and then the degrees of freedom for total is N minus 1. Okay, then we take the sum of squares divided by the degrees of freedom, we get the mean square. Okay, mean square. Mean square for treatment is MST. Okay, mean square for the error is MSE. So again, we're going to take the figures later. And finally, our F. Okay, our F is basically, we divide the MST over the MSE. So as for now, we can just leave our ANOVA table empty. And now I'm going to show you the steps to calculate each and every one of these items. Alright guys, so what you need to do first is to just copy back the table from the question. Then once you have this, we are going to create another column called total. Okay, so we're going to use this later. Now from here, what we need to do is we need to find the sum of all of these columns individually. Okay, so we're going to put here the sum of the column. Just add them all up. So you can use your calculator now. Add them all up. You'll get here 25. And add all of this up. we'll get 31. Add all of these up, you'll get 41. So now this is where we use this new column, okay? I want you to add them horizontally. Add 25 plus 31 and 41, you can get, or you will get 97, okay? Now the next step is to count how many of the items are in each plans, right? So n, so here we have 5, and here's also 5, and here's 5. Again, we add horizontally, here's 15. So what are we doing is basically we're going to calculate the mean, okay? We're actually going to calculate the mean for each column. So this is our x bar subscript c. So how to do that? The sum of the items divided by the total number of items. 25 over 5, you get 5. 31 over 5, you get 6.2. And 41 over 5, you can get 8.2. Now here, we do the same for the total. 97 over 15, we get 6.47. So this one, guys, is our grand mean, okay, or x bar subscript g, right? Okay, let me just zoom out a little bit. So this is our x bar subscript g, or this is our grand mean, and these are our respective column means. Now, it's important, you can just take note, it's important to have this total column, okay? You cannot get the grand mean by just adding these and divide by 3. You can't do that. That's not how averages work. So you need to have this total column to get this grand mean, okay? Okay, the next step is to find the sum of squares for total. Now, if you may remember, okay, what's the formula for the sum of squares total? Okay, each and every x value minus the grand mean. Okay, and then we need to square it up and add it all together. Okay, so this is basically what we're going to do. Now, to find the sum of squares total, you need to construct this table, which is similar to before. I've left it empty for now because I want to show you how it's done. Okay, so this is the table that we've done before. Okay, now let's look at plan A first. Okay, now guys, all of these values are x, okay? X meaning the random variable. These are all of the weight loss that's being recorded, okay, from each participant under each diet plans. Okay, so now here, now let's see the formula just now. X minus grand mean. So here, we're looking at A first, right? So what you need to do is we take the x, which is 5 in this case, minus the grand mean. So what was our grand mean just now? 6.47, right? So minus 6.47. Okay, and because you would want to find the sum of squares, okay, we just square the difference first. Okay, so you can get your calculator. So basically we'll get 2.1609. Okay, do for the entire column. So do for 7, for 4, 5, and 4. Now, once you've done finding the squares of all of the differences between each of these values, okay, we can proceed with Plan B and Plan C. Again, just in case if you're quite lost in what's happening, okay, how do we get all of these figures? What you need to do is we take each and every one of these values, okay, we minus the grand mean, which is 6.47. Okay, each and every one of them, we minus 6.47, and then we square it. Okay, we square it. Okay, now next, this is basically the square difference lah. Okay, so these are the square difference. What we need to do now is to find the sum of the square difference. Okay, so to find the sum of the square difference, we can go by column, right? So the sum by column, we add it all up. So you can take a calculator, add all of these up. You get 16.8045. Here, the sum of the square difference is 3.1645. And here, the sum of the square difference is 17.7645. And because we want the sum, yeah, so what we need to do is we just add it horizontally again. So this 16.8045 plus 3.1645 plus 17.7645, what we'll get is 3773. And this, guys, would be our sum of squares total. Next is to find the sum of squares for the error. So the formula is, again, take all of the x values, but this time we minus the average of each column. Okay, and then we square the difference and add it all up, similar to before, right? So here, again, I've left it out empty, so I'm going to show you how it's done. Okay, again, this is the original values, yeah? So look at A. And the first number is 5. So we're going to take 5 here. But now, instead of minusing the grand mean like before, we're going to take the mean for that particular column that 5 belongs to. So if you look here again, look at this plan A. Okay, look at plan A. This is 5 just now. Plan A, the average for this plan A column is 5. Okay, the average is 5. For plan B, the average is 6.2. And for plan C, the average is 8.2. So what we're going to do is for each and every one of these columns, we're going to take the respective individual x values and minus the respective average or mean of that column. 5 minus 5 in this case, and then square it. So here we'll get 0. Do the same for the entire column for plan A. Once you find the squared difference for each column, what we need to do is find the sum. Okay, so we add all of these squared difference. Here's 6. Add all of this squared difference, we get 2.8. Add all of this squared difference, we get 2.8. So when we add it all up, we'll have the sum of squares. 6 plus 2.8 plus 2.8, we will get 11.6. Okay, so this one, guys, is basically our sum of squares for the error. Now, since we have both the sum of square total and sum of square error, it's very simple to get the SST now, okay? To get the SST, it's simply sum of squares, the total, minus SSE. So it's just 33.73 minus 11.6. So we'll get 26.13. All right, so all of these values, now we can go ahead and put it in the ANOVA table. Okay, so we're back at our ANOVA table. Now all we have to do is just fill in the blanks. SST just now was 26.13, right? And then our SSE was 11.6. If you add this together, we'll get our SS total, which is 37.73. Now for the degrees of freedom. Normally it's easy just to do the n-1 because we know the total sample size is 15, right? So 15 minus 1 is 14. K is referring to the number of categories. We had 3 categories just now, right? Plan A, Plan B, and Plan C. So 3 minus 1 is 2. N minus K is just basically 14 minus 2 here. Okay, that's another way to do it, which is 12. Or N here is basically 15 minus the category size 3. So 15 minus 3, again, you get 12. Next is to find the mean square. Okay, mean square is basically you take the sum of squares, divide it with the degrees of freedom. Okay, so we take 26.13 divided by 2, so you will get 13.065. And here, mean square for the error, we take SSE, 11.6, divided by the degrees of freedom for SSE, 12, so you'll get 0.967. Finally, we want to calculate the F test statistic, so it's just MST divided by MSE, 13.065 over 0.967. Our F test statistic is 13.51. Now move on to step number 4. Okay, we want to write down the rejection area. So we know that since it's an F distribution, it's always positively skewed. Therefore, this is our rejection area where we reject the null. Alpha is 5%. Okay, and here is where we do not reject the null hypothesis. Okay, now we want to see what is our critical value. Very simple. Okay, we'll go back to your ANOVA table, guys. So this is the degrees of freedom for the numerator. This is the degrees of freedom for the denominator. Go and look at your F table. So this is the F table at 5%. Okay, make sure you're looking at the right table. Now, just now we mentioned that the degrees of freedom for the numerator was 2, and the degrees of freedom for the denominator was 12. So you just look at 2 and 12, and we get 3.89. Yeah, so 3.89 is basically our critical value. Now that we have the critical value, we can write down our rejection rule. okay, which is to reject the null if our F test statistic is beyond or more than 3.89. Okay, so step number 5 and 6, we just compare our test statistic just now, which is 13.51, against this rejection area. So where is it? It's somewhere here, yeah? Okay, so we can see that since the test statistic falls in the rejection area, okay, rejection area, what we do, we reject the null, okay? So we reject the null hypothesis, right? Reject the null hypothesis, and we can conclude that, okay, go back to step 1, since we reject this, we are accepting the alternate, we can conclude that not all of the population means are equal, okay? Or if you want to, you know, be more specific in terms of the context of the question, you can conclude that there is a difference in the mean amount of weight loss. Among the 3 diet plans. Among the 3 diet plans.